this is a bit of a review of what we went over last week. Now, looking at this profile here of Earth's atmosphere, most of the mass of Earth's atmosphere is within the lower 100 kilometers above sea level. And Earth's atmosphere is approximately 130 kilometers thick, which is about 2% of Earth's radius. Now, that's a very thin shell. That's a thin covering. And Earth's atmosphere is in a state of hydrostatic equilibrium. So remember that this means the force of Earth's gravitational pull, pulling down of the atmosphere, is balanced by the pressure gradient force, which wants to push the atmosphere outward. And last week I said that the atmosphere would explode off into space if it only had the pressure gradient force. So it wouldn't be quite that dramatic. The atmosphere would just slowly diffuse off into space, and we'd lose it over a bit of time. And if the gravitational force outweighed the pressure gradient force, the atmosphere would just collapse in on us. And so it's this happy medium that enables us to even live on Earth's surface. And if you watched the videos last week, you would have saw that our bodies, the pressure within our own bodies, is also in equilibrium with atmospheric pressure. So we push out on the atmosphere with the same pressure that the atmosphere is pushing on us, right? If our pressure were greater than the atmosphere, we'd explode. If the pressure pushing down on from the atmosphere onto our bodies were greater, then we'd smush, we'd implode, right? All right, so now moving onward. Let's look at the composition of the atmosphere. Now, some of this should look familiar to you if you've already opened up Lab 1, but the atmosphere is composed of both permanent and variable gases. Now, the blue box on the top of the screen there shows the permanent gases, and that is in the dry gas percent by volume of the atmosphere. So this is not considering water vapor. That's what the percentages are if there was zero water vapor. Okay, because the percent water vapor varies in Earth's atmosphere depending on where you are. So the Earth's atmosphere is about 78% nitrogen, 21% oxygen, less than 1% argon, and then a small percent mixture of neon, helium, krypton, xenon, and hydrogen. Now, those gases pretty much remain at that proportion at those percentages in Earth's atmosphere. As we get into paleoclimate, you'll see how things have changed throughout geologic time, but speaking on the human time scale, those don't change very much. Now looking at variable gases. Variable gases change. Their concentrations change in the atmosphere. So water vapor, that's variable. Everywhere in the atmosphere it can range from 0 to 4% by volume. Carbon dioxide is about 0.04% now. It keeps going up. And then we have a bit of methane, nitrous oxide, ozone. These are all greenhouse gases. And as you'll see in the video coming up soon explaining the greenhouse effect, that the structure of these molecules in compounds are really good for absorbing long-wave radiation emitted by Earth's surface. Now, looking here, we can divide the atmosphere into a few different layers. Let's first look at the homosphere versus the heterosphere. Now, the homosphere is well mixed. So it's turbulent mixing. So one really easy way to think about turbulence is if you turn on your kitchen sink faucet really on a low pressure, and you can see the water trickles out clearly. You can see right through the water. It's clear. That is called laminar flow. Then you crank up the pressure in the water, and it comes out all white and you can't see through it. That's a turbulent flow. So there's eddies, there's lots of mixing going on. So in the homosphere, we have this turbulent mixing. And so the gases are really well mixed. You see that we have some dinitrogens down here, some molecular oxygen, some water, some argon. So just some of the main components of the atmosphere are depicted there. And most of the density, most of the mass of the atmosphere is in the lower 85 kilometers. And now the atmosphere gets really, really thin as you move upward. So what does that mean? Pressure is greater near Earth's surface. There's more atoms and molecules. There's more stuff there. So it's going to have greater pressure. As you move upward, there's not as much. So it's going to be lower pressure as you move upward. And into the heterosphere, there's not turbulent mixing. So things are not mixed very well. And as you get really high up in the atmosphere, in the ionosphere, the sun is actually reacting with some of the molecules and atoms up there to separate off electrons. So that makes them charged ions. So these are negative, electrons are negatively charged. So those would be anions. Cations are positively charged. Now, I want to spend a little bit of time with you looking at this closely. Now, let me get my pen working if I can find it. Let's see. Get a pen. And we'll do magenta. Now, let's look at this graph a little, because when there's all these things going on, it might be a little challenging to interpret. So on this first y-axis here, there are two y-axes. This would be called the primary y-axis. We have pressure is increasing downward, because on the secondary y-axis, we have altitude or geometric height. So this is height above sea level, altitude above sea level. So that's increasing as we move upward. So as we move down in altitude, closer to sea level, pressure increases, is what that is showing. Then on this x-axis over here, we have temperature. All right, and we have increasing temperature moving to the right, and this is shown both in degrees Fahrenheit and in the absolute Kelvin scale. So Fahrenheit, that's British units, and Kelvin is metric system. All right, now we live on the surface of Earth. So we live in the troposphere, right? This is the air that we're in contact with. So it's at high pressures, right at Earth's surface, and also it's in contact with Earth's surface. You're going to expect that it's going to be at a high temperature as well, relatively speaking. So as you move up in the troposphere, pressure decreases and temperature decreases. Then we hit a pause. And with this pause, we have the tropopause, where we have a line of constant temperature. This is called an isotherm, constant temperature. All right, so in the tropopause, we have the jet stream, and all our weather occurs down below in the troposphere. And just for reference, Mount Everest is about 29,000 feet tall, okay, so it's in the troposphere, but we can get the cumulonimbus clouds up in the tropopause. Now, let's look at the stratosphere. In the stratosphere, we have ozone, and good ozone lives in the stratosphere. The bad ozone lives in the troposphere. We don't want to be interacting with that ozone, but in the stratosphere, the ozone shields Earth's surface from harmful ultraviolet radiation, so it's helpful up there. Okay, so it reacts with sunlight and it shields us from UV radiation. And so as we move up in altitude through the stratosphere, temperature starts to increase again because of these reactions. And then you'll notice midway through the stratosphere, we've hit a point where down below we have 99% of the mass of the atmosphere. So most of the stuff in the atmosphere is down in this lower 30 kilometers. All right? And what this black bracket is showing, it's showing the part of the cross-section that I depicted on the last page, because I wasn't even showing everything there. All right, so then we hit another pause, so we have an isotherm, an area of constant temperature, and I have no idea where that just went. Hold on, I will bring it back. Okay, so then we hit the tropopause, which is another region of constant temperature. And where were we? Sorry, we're at the stratopause, area of constant temperature. And then we move upward into the mesosphere, and we're decreasing in temperature again. We hit the point where we have the highest level, where we have some microorganisms up there. And sorry, bear with me a second here. All right, and mesosphere is the coldest region of the atmosphere, so it protects Earth from meteoroids. So this is where they burn up, in the mesosphere, and then we have another pause, so we have constant temperature, and then as we get to the outer layers here, we have a lot of UV radiation turning into heat, really making it hot up near the top of Earth's atmosphere. So that is the thermosphere. All right, so it's really just to think about it. So if you just start with what you know, near the surface, in the thermosphere, it's warm. Then we hit a temperature pause, and then we increase back in temperature, then we decrease. So it does this kind of snaking pattern, but there's always a pause between each layer. Good ozone lives in the stratosphere. We have weather in the troposphere. We live in the troposphere. All right.